So one of the tools on topic 13 is process proving and problem solving. So how do we prove our quality? Or how do we prove our process is in control? So we have two things we're going to be measuring. So we have random variation and systematic variation. So random is just that, it's random. We don't know why it's happening or how to predict for it or how to even correct for it. But the systematic one, we are able to figure out the cause, the root cause of that. And we have some tools that we can use to find what's causing that. So we have what's called the process capability ratio. So is our process capable? So is the supplier's process capable of meeting our quality requirements? This is something that they should be doing on their own based on the specifications we gave them. So we run a pilot test under the actual operating conditions. So actually start up the manufacturing line, see what happens, and then actually do the measurements. Measure the output against a quality standard. We need to do that to figure out, is it what we want? Is it meeting our specifications, our engineering specifications? So we have this formula here. So we have C sub P equals the absolute value of our upper specification limit, subtracting our lower specification limit, and dividing that by 6 standard deviations. I know it seems complicated, but it's really not that difficult. So what does that actually mean though when we do that? Well, it actually is what is acceptable divided by what is actual. That's what it really comes down to. So the acceptable, if you say that you need something that is 12 inches long, give or take an inch, well, your upper specification limit might be 13 inches, that's that inch, and the lower might be 11 inches, your lower specification limits. So then you're going to divide that by the actual result that they're getting. So how do we know if their process is actually in there? Well, the CP value, if it's less than or equal to 1, you see how wide this bell chart is? That's what we're looking for here, how wide it is. And if it's greater than 1, you see how narrow it is. So these lines here would be your upper and lower specification limits. So we're looking at where this chart, where the bell chart is, for this line and this line, we want them to be between our specification limits, or at least a majority of it, depending on what sigma level we're going for. So our process capability ratio, we're actually running the processes under actual operating conditions. We're started the manufacturer line. We're measuring it, so we're doing that. And now we need to figure out our C sub PK. So we're adding in K here. So we're adding in mu. And then we have our upper and lower specification limits. Well, this is actually going to tell us if we're left or right of our specification limits. And you can tell this when you look at it. When you look at the numbers that you're getting, you can tell, well, everything's over here, or everything is over here, or we're right in the middle. We can tell that. All right, so another thing we do here is the Deming's, or Edward Deming's PlanDoCheck Act improvement cycle. So we make a plan of how we're going to go about this situation. We're going to actually do the plan, execute the plan. We're going to check our results, and then we're going to evaluate our results to develop a new plan. And then we start the plan phase all over. It's a continuous cycle here. And every time you do it, you should be improving. But to get to the root cause of some problems, we need to use the Ishikawa cause and effect diagram. So this, we have certain categories that are always on the fishbone diagram. That's what it's also called. It's a fishbone diagram. So we have our problem right here. Surge in defective parts. Well, we have these required categories that we always put on here. People, methods, machines, environment, materials, and measurements. So what might be the people cause defective parts? Could it be poor training, fatigue? Could it be something else? Maybe too much coffee? All these different things could be impacting the people, which would then cause the defective parts. So I hope you see how that's working out. Now let's look at environment. Well, what affects the environment? Well, the temperature, if it's hot, so when it's not supposed to be, or it's cold when it's supposed to be hot, and the location. What about if you're in a tropical environment, you might have to deal with humidity. Well, humidity might be bad for the product you're making. So all these different things need to be considered, but you always put these categories on the fishbone ribs, and then you do the lines off it. And then finally, we have the Pareto diagram. So if you guys remember the 80-20 rule, 80% of your problems are caused by 20%. So here we see the cumulative percentage line. We have 79%. 80-20 is not a hard and fast rule, but you see here, this looks like this is 80% or 79% of our problems. So when we look at our problems, these over here just comprise 20%, so we're not going to focus on those. If we focused on the methods and the people, we can take away 80% of this and leave only 20% of our problems. Then we do it again, which might be the machines and in the environment. And we keep doing that until we get these down so low that it doesn't even concern us anymore. But we still keep an eye on it. So this was some tools that we can use to evaluate quality. Now, some of them you'll learn a lot more in our quality class, and I hope you guys will progress to there, and I look forward to seeing you guys in the next topic.